slightly resolved. Here it is essentially overlapped. Here it is slightly resolved. And there you can expect to have the two A values based on the two isotopes. So you need to do some kind of Gaussian analysis to figure it out. And that can be done without much difficulty. Now the next example, what we have given, which is the similar kind of example on platinum based system, where you have two isotopes, 95, 96, two isotopes. And if you see the isotopes, their ratio, their isotopes means magnetically, one is magnetically inactive isotope and one is magnetically active isotope. And this is your I equal to half. And if you look at the magnetically inactive, that means I equal to 0. So you should expect to have one line. But remember, this one line is not, it looks like the free radical line, but actually not the free radical line. I already talked it about that, that if you have a very symmetrical setup around the metal centers, okay, and there won't be any additional distortion at the molecular level, so you will have one line spectrum. And if you have one line spectrum, only difference between the metal complex based or metal based one line spectrum and the organic radical based one line spectrum, that is the bandwidth. Bandwidth means the difference in magnetic field, that means in Gauss from this point to this point. For field radical case, it will be very, very sharp. Okay. But in metal complex based isotropic situation, it will be rather broad. So it is not very difficult to understand. When you start practicing it, looking at the spectrum, you may be initially a bit confused, but if you do the manipulation properly, then you would realize that you are dealing with radical or you are dealing with metal-based situations. Now here, since this particular isotope, there is no I equal to 0, and here if you look at the I equal to half, and so you can expect the two lines. So basically you can consider based on the factor of the ratio by 2. Okay, that is abundance by 2. That as far as the intensity is concerned, intensity would be inversely proportional to the number of lines you are getting out of that particular isotope. Okay, so since this isotope gives you the two lines, so it will be 1 by half, and the ratio is inversely proportional. So the ratio is essentially this by this into 1 by half. Okay, and then you will be seeing, so much smaller line. And if you are lucky enough, if your situation or system means I'm talking about the molecular system, is not very cumbersome, and also your spectrometer is quite good in terms of its resolution or sensitivity, then you would be getting exactly the same ratio. The ratio what we could see over here, that would matching. So 17% with respect to the I equal to 0 line. Okay, and that you would be seeing in 17 plus 17, 34. Okay, so under that context, if you take little bit complex situation, molybdenum situation, where you will have, you see that 26% having I equal to 5 by 2 and 75% nothing, and then 5 by 2 means 6 lines. So basically 1 by 3 and 1 into 1 by 6. That means 18th. Each line intensity would be the 18 times smaller than the parent line, this one. So you could see much smaller lines compared to this one, right? Okay. So, as I said, that if your system is good enough, including the instrument, you will be getting exactly what you can expect out of your calculations. But as you know, life never goes in a linear fashion. Sometimes it is good, sometimes it is not so good. But if you are aware of, we can handle the situation in a fairly reasonable or fairly good way. Now, these examples we talked about also, And there only one good point I tried to mean, that again the same situations. So you would be getting 4 lines, and each line would be split into 3 because of the fact of the metal nitrine, that in interactions. But this example highlights the fact of the covalency, okay, beyond the point of the crystal field theory uh, to the molecular orbital theory. This is one of the finest example. Here we end it. Now another example, if you take, this is the similar example, but the point is, as I said, that your ESR, you cannot have the linearity as far as the quality of the results are concerned. Now, if you look at the similar kind of situation of chromium 5 situation, that means D1 situation, here you have taken the porphyrin as the macrocyclic ligand around the chromium center, and the 6 coordination, naturally one solvent is there. If you record the EPR, then what will happen? You will have chromium based one line, that you will never miss it, okay? And this one line would be further splitted into there are 4 nitrogens which are directly bonded. These are all covalent bonding, okay? So you won't miss it. A nitrogen 100% abundance. So 2 into 4 into 1 plus 1, 9 lines, right? So the primary lines which is coming out of this chromium, that would be being splitted into 9 lines. You could see there are 9 lines are over here. One could also anticipate that chloride is also 3 by 2, okay? But if you look at this spectrum carefully, 1 2 3 4 sorry 1 2 3 4 5 6 7 8 9, okay? The chloride did not interact with the chromium center. Well, one could argue that why it is not so. Well, at the X-band level, chloride has not been resolved. Even if you do the simulation, you won't see any further splitting because of the chloride. Chloride is 3 by 2, don't forget. There's an additional 4 lines one could expect. That does mean that the chloride distance, okay, though it is a covalent bond, but distance is slightly longer than the distance which is necessary to have the interactions at the metal electron and the nucleus spin of chloride. And indeed, if you record the crystal structure of this molecule, you will see that this metal chloride distance is slightly longer than what one could estimate out of the standard condition. And that is why it is not being reflected. But there are many occasions, and I will be also talking about that at the later part of today's talk, that how chloride could take part into the your super hypercurrent splitting profile of that compound. Okay, so but here, if we well, if you are not very careful or very enthusiastic, we would only say, unlike the previous case, that chromium other isotope, which is though 10%, which has have no impact on this spectrum. But if you are enthusiastic in understanding the spectral profile, then you will see that there is something over here and something over here. Actually, we should